This is lab 2. So we're going to be revisiting the charged tape experiment. And so the purpose is to once again calculate the magnitude of excess charge on a piece of tape, but this time treating the charge as being evenly distributed over the tape instead of treating the tape as a point charge. And so once again, fundamental principles here are Newton's second law, the Coulomb's law, which can be used to calculate electric force given charge and separation of charges, and the concept of superposition of forces, which is that we can sum up all of the forces to find net force. And so the excess charge ended up being 5.04 times 10 to the negative 4 newtons, which was less than in our original lab. So just a quick reminder from lab 1, tapes were given a charge and they have opposite charges. So one tape was held below the other they have the same charge. So one piece was held below the other and this caused them to separate. And so using the measurements and separation distance, we were able to calculate the gravitational force on that top piece of tape, and since it's not in motion, use that to calculate the electric force. From there, calculate the charge on the tape based on the area of the tape. And so we found that the excess charge was 1.6 times 10 to the negative 8 coulombs. So for this model, we split the tape up into segments, and every segment is treated as a single point charge. So then we are able to sum up all the forces on each of those segments to get our net force. And we're assuming that there's no air resistance and completely even charge distribution. So as far as the actual code, these are the initial conditions based on our experiment. So the mass of the tape, the charge of the tape that we calculated from our last experiment, and then the length of the tape and the distance. And so then here we define an electric field based on observation location and position of charge. And then this is how we create a line of charge. So this is where we split the tape into a bunch of different segments. Here, this is distributing the charge evenly into a bunch of point charges in each segment, with each segment having the same point charge. Again, distributing those masses based on the number of segments that we split the tape in. And so then actually creating the tape, these distances and lengths are based off of the separation distance and then the length of the tape itself. And I chose to split the tapes into 100 segments, and that being said, the more segments we have, the more accurate we get. So essentially what we did here was iterated through every segment of the tape, and here we were trying to find the force on the top tape. So iterated through every segment of the bottom tape, and then from there iterated through every segment on the top tape and calculated the force on each segment of the top tape. And then we summed up all of the forces for the top tape, and that was how we got our net electric force. And so what we found, this is what we expected. There's an upward force from the bottom tape on the top tape. Again, since the gravitational force is downwards, we would expect the force from the bottom tape on the top tape to be upwards. And so, quick discussion. I made a typo here. This was supposed to be times 10 to the negative 8th, so actually the force on this model was much larger. And the reason that these forces, excess charge. And the reason that these differ is because we're using, okay, I'm sorry, I said that wrong. Yeah, this is the magnitude of the charge. And the reason that these differ is because the model that segments the tape more accurately accounts for the actual electric force.